Welcome to Formula 1 Maths. This is Mixed Exercise 4.01, GCE A-Level, Applied Maths, Year 2. Mixed Exercise 4.01 is on moments. We've got 3 questions to answer. Question 1. A uniform rod, PQ, has weight 300 newtons. It hangs in a horizontal position supported by 2 light inextensible strings at R and S, where PR is equal to 1.4 meters and RS is 1.5 meters. The tension in the string at S is 220 newtons. Calculate A. The tension in the string at R. B. The length of the rod. So this is a rod, and this and that are the 2 light inextensible strings at R and S. We need to put in the forces acting on the rod. There's a tension of 220 newtons acting in the string at S. There's also tension T in the string at R. There is a weight of 300 newtons acting at the center of the rod because the rod is uniform. For A, because the rod is in equilibrium and it's not moving up or down, we can say that total upward forces is equal to total downward forces. That means T plus 220 is equal to 300. We can then rearrange and solve and get T is equal to 300 minus 220, and that gives us T is equal to 80 newtons. For B, we need to take moments, and I've decided to take moments about P. So we need to find the respective perpendicular distances from the lines of action of the various forces. We know that T is equal to 80 and PR 1.4 meters, RS 1.5 meters, and because the weight acts right at the center, I'm going to say let the distance from P to the center be X. So let's call that X. We are now in a position to take moments about P. But let's see the nature of the moments that will be produced by the various forces. The 80 Newton force will produce an anti-clockwise moment about P here. So will the 220 Newton force. The other force, 200 newtons, will produce a clockwise moment about P. To avoid using negative moment and positive moments, we are going to say the total anti-clockwise moment will be equal to the total clockwise moment. So we can take moments now, and we are going to end up with this equation here, where 80 times 1.4 plus 220 times 2.9, because 1.4 plus 1.5 is 2.9, will be equals to 300 times x. So if you simplify this, you're going to get 112 plus 338 is equal to 300x. Simplifying will give us 750 is equal to 300x. And solving for x will give 5 over 2, which is 2.5. But we are looking for the length of the whole rod. And the whole rod will be twice the length of x. So the length of a rod will be 2 times 5 over 2. I can cross out this one, and I'll end up with 5 meters. So that's question 1. Question 2. A uniform beam, AB, of length 5 meters and weight 200 newtons, rests in equilibrium on supports at C and D, where AC is 0.5 meters and BD is 1.5 meters. A particle of mass 10 kilograms is attached at A. Find the largest weight, W, which can be applied at B for the beam to remain in equilibrium. So let's draw our diagram. So this is a beam and these are supports at C and D. The weight of 200 newtons acts right at the center of the beam because the rod is uniform. There's also a reaction force at C, which we will call R1, and then a reaction force R2, which occurs at D. There's also a weight of 10 newtons that is attached to A. We need to apply a weight of W at B. We need to take moments now. Before we take moments, we need to find the respective perpendicular distances of the lines of action of the forces. So we know that AC is 0.5 and BD is 1.5. This point here is the center of the beam. That means from A to this point is 2.5. That makes the distance from C to this point 2 meters. Similarly, from the center to B is 2.5 meters. But BD is 1.5. That means from this point, the center to D is 1. I'm now in the position to take moments, but we are required to find the largest weight W that can be applied at B. For the largest weight, this will occur when the beam is at the point of tilting at D. In that case, the reaction at C will be equal to 0. So we don't have to worry about the moments due to R1. I've decided to take moments about D. Before we take moments, let's look at the nature of the moments that will be produced by R2, the 10 Newton force, the 200 Newton weight, and W. Taking moments about D means the 10 Newton weight will produce an anti-clockwise moment, and the 200 Newton weight will also produce an anti-clockwise moment about D. But W will produce a clockwise moment about D. We don't want to use negative and positive moments, so we are going to say the total anti-clockwise moment is equal to the total clockwise moment. That will give us this equation here, because 10G times 3.5, because 0.5 plus 2 plus 1 is 3.5, plus 200 times 1 will be equal to W times 1.5. Reducing this equation gives 343 plus 200 is equal to 1.5 W. Simplifying gives 543 is equal to 1.5 W. And solving will give you 362 newtons. And that is the greatest weight that can be applied at B. Question 3. A uniform ladder AB of length 4 meters and mass 20 kilograms rests against a smooth vertical wall with its feet on a rough horizontal ground. The coefficient of friction between the ladder and the ground is mu. The ladder is inclined at 60 degrees to the horizontal. If a boy of mass 30 kilograms climbs up the end B without it slipping, find the value of mu. So let's do our diagram. So this is our smooth wall and this is our rough horizontal ground. Our ladder AB is inclined at an angle 60 to the horizontal. The ladder has a weight of 20 Newtons. That will be acting right at the middle or center of the ladder. That means the distance from A to the center is 2 meters, and from the center to B is 2 meters. There will also be a force of 30 Newtons acting on the ladder at B due to the weight of the boy. The ladder is in equilibrium, so there will be a reaction force due to the rough ground, and because the ground is rough, there will also be frictional force F acting towards the wall, because if the ladder slips, it will slip away from the wall. That means the friction will be acting towards the wall. The wall is smooth, so there will be no frictional force along the wall, but there will be a reaction force which we will call S. So these are all the forces acting on the ladder. We need to take moments to be able to calculate mu. Before we take moments, we will need to find the respective perpendicular distances of the lines of action of the force from a particular point about which we will take moments. So I will take moments about this point A, and so I will calculate the respective distances of the lines of action of the forces from A. To do that, I'll drop a line here like that, And immediately I can see that the distance, this distance here, which is the perpendicular distance of the line of action of this force, will be 2 cos 60. The perpendicular distance of the line of action of this force from A will be 4 cos 60. Similarly, the perpendicular distance of the line of action of this force from A will be this distance here, which will be 4 sine 60. Before we take moments, there are a few things I need you to take note of. First of all, the frictional force is equal to mu r, mu times r. We need also to resolve forces vertically and horizontally. The ladder is in equilibrium, so the forces, the vertical forces are R acting upwards, 20G acting downwards, and 30G acting downwards. Because the ladder is not moving up or down, total upward forces must be equal to total downward forces. That means R is equal to 20G plus 30G, which is equal to 50G. Resolving horizontally, there are only two forces acting horizontally: the reaction force S and the frictional force F. And because the ladder is in equilibrium, it means S is equal to F. But we already have established the fact that F is equal to mu r. That implies that S is equal to mu r. We know the value of r, so it means S is equal to 50G mu. We can now take moments, and I've decided to take moments about A, as I mentioned before. And taking moments about A means that I do not have to worry about R and F, because their respective perpendicular distance from A is 0. So let's look at the nature of the moments of the rest of the forces left. For the first one, the 20G Newton force will produce a clockwise moment, and the 30G Newton force will also produce a clockwise moment. But the reaction force S will produce an anti-clockwise moment. Again, we do not want to use negative moments and positive moments, so we're going to say total clockwise moment is equal to total anti-clockwise moment. And that means 20G times 2 cos 60 plus 30G times 4 cos 60 is equal to S times 4 sine 60. If you replace S with 50G mu, you get this equation here. I can now simplify this equation by multiplying out the various terms to obtain this. I can simplify now by dividing every term by 10. And that means crossing this 0 out, that's 0, and that's 0. I can further simplify by dividing every term by G, and it also means crossing out dg, dot G, and dot G. And this reduces the whole equation to 4 cos 60 plus 12 cos 60 equal to 20 mu sine 60. I can reduce this equation further by dividing every term by 4 to get cos 60 plus 3 cos 60 equals to 5 mu sine 60. Cos 60 plus 3 cos 60 will give 4 cos 60. And so we have 4 cos 60 equals to 5 mu sine 60. Rearrange to solve for mu, and we're going to get 4 cos 60 over 5 sine 60. Introducing a little pure maths here, we yield 4 over 5 tan 60. And evaluating this will give us mu is equal to 0.46. And that is the value of mu. This is the end of this set of questions on mixed exercise 4.01. Thank you for watching.